Good evening to everyone and all. It's my great pleasure to introduce our chief guest. Yeah, good. Yeah. Yeah, good. It's a pleasant evening to everyone and all. A pleasant evening to one and all. It's my pleasure and privilege to welcome you all for the inaugural function of FDP on emerging trends in electronics communication and networking technologies, organized by the Department of Electronics and Communication Engineering, Sri Vidyanaketan Engineering College, Tirupati. Thank you so much, sir, for your concern, support, and encouragement. Now I invite the Vice Principal, Dr. T. Nageshwara Prasad, sir, to share a few words. கனெக்ட் பண்ணிட்டாருங்க. இதையும் கனெக்ட் பண்ணிட்டேன், சப்போர்ட்டுக்கு இதையும் டேபையும் கனெக்ட் பண்ணி வச்சிருக்கேன். இது ஜூம் ஒர்க் ஆகவே மாட்டேன்ருச்சு. சரி, அதனாலதான் சரி. இப்பதான் போட்டுக்கிட்டேன். ஒரு 5:15 எடுத்து 2 கனெக்ட் பண்ணி இதுல கனெக்ட் ஆச்சு. 5:45. ஆக்சுவலா ஹெச்ஓடி சொன்னதுக்கு எதுவுமே இல்லை. சொன்னது கூட மாத்தி விட்டுட்டு இந்த மாதிரி நான் கொடுத்துருக்கேன் பாரு. வெல்கம் நோட்டு ரமணா பேசுறாரு, நாகேஸ்வர் பிரசாத் பேசுறாரு. ரமணா கருத்து நாகேஸ்வர் பிரசாத் பேசுறாரு. வெல்கம் வந்து ஹெச்ஓடி பேசுறாரு. அதுக்கப்புறம் வந்து டீன் ரமணா கூப்பிடுறான். அதுக்கப்புறம் ஃபைனலா வைஸ் பிரின்சிபல் கூப்பிடுறான். அப்படிதான் கூப்பிட முடியும் இல்ல? கரெக்ட் தான் போட்டுட்டு கடைசியில ப்ராப்ளம் இது ஸ்டார்ட் பண்ண சொல்லிடுறாரு. என்னன்னா காலையில இப்போ கொடுத்துருக்கு எல்லாத்தையும் சரி சரி கேட்டு காலையில எடுத்து சிம்பிளா ஒரே வார்த்தை நோ நீட் ஆஃப் தட். ரெண்டாவது கேக்குறேன் கேன் ஐ ரிமூவ் சம்ething? Yeah, I told you that. அப்படிங்கறா we are not celebrating one day event. We are not celebrating one day event. அப்படிங்கறா we are not celebrating one day event. எதுக்கு one day event? அதாவது full day event இல்லங்கறதா.
Sir, Ashok sir. Ashok sir.
Madam.
கேக்குதுங்களா? Sir, Ashok sir. Ashok sir.
Madam.
Sir, கேக்குதா?
Madam, is it audible, ma'am?
Yes sir, கேக்குது sir.
Madam,
sir.
Okay, madam. Screen வந்து என்ன தெரியுது மேடம்?
சரி ஒரு நிமிஷம் சார். ஸ்கிரீன்ல ஒண்ணுமே தெரியலையே.
ஒண்ணு தெரியலையா?
நீங்க வீடியோவை ஆன் பண்ணுங்க சார்.
ஒரு நிமிஷம் மேடம். இப்ப மேடம்?
இப்போ ஸ்கிரீன் தெரியுதுங்க சார். பிபிடி. அந்த இது F5 போட்டுருக்கேங்க சார். பிரசன்டேஷன் சார். அதுக்கப்புறம் சார் சொல்ல நினைச்சேன், கொஞ்சம் எல்லாரும் வந்த அப்புறம் எல்லாரும் வீடியோ ஆன் பண்ணிட்டு ஒரு ஸ்கிரீன்ஷாட் எடுத்துருங்க.
சரிங்க மேடம்.
அது ஒண்ணுதான் நமக்கு எவிடன்ஸ்.
நமக்கு இது இருக்குல்ல மேடம், அட்டெண்டன்ஸ் ஷீட் இருக்குல்ல?
இல்ல அவங்க ஒரு ரிப்போர்ட் கேட்பாங்கல, அப்ப போட்டோ கேட்பாங்க.
ஓ சரி சரிங்க மேடம்.
எல்லாரையும் கொஞ்சம் நீங்க இது ஆன் பண்ணுங்க. நான் லாஸ்ட் வரைக்கும் வெயிட் பண்ணேன்.
ஓகே ஓகே மேடம்.
நீங்க அவரு பேச சொல்றதுக்கு முன்னாடியே வந்து ஒரு பிரிண்ட் ஸ்கிரீன் எடுத்துருங்க.
சரி மேடம்.
எல்லாரையும் ரெக்வெஸ்ட் பண்ணீங்கன்னா எல்லாரும் வீடியோ ஆன் பண்றாங்க. அப்படியே ஒரு பிரிண்ட்.
சோ எல்லாத்தையும் முடிச்சிட்டு கடைசில ஹேண்ட் ஓவர் பண்றதுக்கு முன்னாடி எல்லா பேரையும் வீடியோ எனேபிள் பண்ண சொல்லிட்டு பிரிண்ட் எடுத்துறோம் அப்படினா.
ஆமா, ஏன்னா அது முடியும் போது இவங்க எல்லாம் க்ளோஸ் பண்ணிட்டு போயிடுவாங்க நம்ம ஆளுங்க. சொன்னால கேட்க மாட்டாங்க. அதனால நீங்க முன்னாடியே அவருக்கு கொடுக்க டயஸ் அவர் கொடுக்கறதுக்கு முன்னாடி நீங்க முடிச்சிடுங்க.
சரிங்க மேடம்.
அப்ப நிறைய பேர் இருப்பாங்க, எடுத்துருங்க. அதுக்கப்புறம் அவங்க வந்தாலும் சரி வராட்டியும் சரி அவர் சொல்லி முடிச்ச அப்புறம் க்ளோஸ் பண்ணிக்கலாம்.
ஓகே மேடம்.
ஓகேங்க சார்.
சோ என்ன ஒண்ணுல ஒரு இதுல வீடியோ அப்படி தெரியுது.
இது எனேபிள் பண்ணி வச்சிருக்கேன்.
அதுல டிசேபிள் பண்ணாது. இப்போ எதை மட்டும் நீ வைக்கிற?
வீடியோ
இதுலதான் வீடியோ தெரியுது. அவங்க பாரு கண்ணா பண்ணாங்க.
இப்ப தெரியல. மொபைல் அது சாமி இருந்துட்டு போகுது.
அது பாட்டு இருந்து போய் மொபைல் விட்டுரு.
சார்ஜ் போட்டு அது சாமி
சரி இப்ப இதுல என்ன கனெக்ட் பண்றியா?
இல்ல வேணாம், வேணும்னா கனெக்ட் பண்ணிக்கிறேன்.
சரி ஓகே. அப்ப நான் கனெக்ட் பண்ணிட்டா?
நீ கனெக்ட் பண்ணு. ஏன்னா சைடுக்கு இது வச்சிருக்கேன். இனாகிரேஷன் ஃபங்க்ஷன் முடிஞ்சுனா இது போனாலும் போயிட்டு போகுதுன்னு சொல்லி மொபைல் அது சாம போட்டுட்டு.
ரெக்கார்டா எதுல ரெக்கார்டு போட்டிருக்க?
இதுதான் ரெக்கார்டா.
அதுல
ரெக்கார்ட் ஆகாது. நம்ம ரெண்டுமே ரெக்கார்ட் பண்ணலாமா?
இல்ல அதுலயும் ஒண்ணு இப்போ ஒண்ணுல மொபைல் விட்டுரு.
மொபைல் விட்டுட்டு இது மட்டும் தான் ரெக்கார்ட் ஆகும்.
இல்ல சோக்கு அதுவும் ஒர்க்கிங் கண்டிஷன் தானே.
அது ஒர்க்கிங் கண்டிஷன் தான்.
அதுலயே இதை லாகின் பண்ணு.
3 தடவை லாகின் பண்ணலாம்.
மொபைல்ல லாக் அவுட் பண்ணிடு. அதுல லாகின் பண்ணு. 3 இதுல லாக் அவுட். மொபைல்ல லாகின் பண்ணீங்கன்னா இது டிஸ்கனெக்ட் ஆயிட்டே இருக்கும்.
ஓ இதுல இருந்து டிஸ்கனெக்ட் ஆயிடும்.
இது வெளியே வந்துரு. அதை மியூட்ல போடு. வீடியோல இது பண்ணு. இங்க நீ ஆடியோ மியூட் பண்ணிருக்கேன்னு பாரு. ஏன் அது இப்படி வருது?
இது போனோம்னா அதான் சொல்றேன் நேத்து இது கேன்சல் கொடுக்குறோம். எக்ஸாம் லீவ் மீட்டிங்ல குவிட் ஆகி போயிருச்சு.
ஆமா குவிட் ஆயிடும். அது கீழே கண்ட்ரோல் அது ஸ்கிரீன் ஷேர் ஸ்டாப் பண்ணு. ஸ்கிரீன் ஷேர் ஸ்டாப் பண்ணு. இப்போ வருது. இதுல மைக்கை மியூட் பண்ணு. கேக்குதா? ம்.
sorry phone பண்ணுவா. Hello.
Actually, record unmute பண்ணு. Okay.
Dean sir.
Good evening, sir.
Sir, good evening, sir.
Good evening.
Sir, Dean sir, good evening, sir.
Good evening. Good evening.
Yes, sir.
Hello, Dr. Ashok.
Ashok, you are in mute.
Yeah, Swapnil. Hello. Okay. Please unmute.
Hello,
Yeah. Good evening. Good evening.
can you hear me?
Yeah, yes. Sir, can I proceed, sir?
Okay.
Yeah, yes, sir.
You already time is 9:15 or just 9:14. Just for 2 minutes and you can start.
Yeah, okay, sir.
You wait for 2 minutes.
Yeah, okay, sir. A pleasant evening to one and all. It is my pleasure and privilege to welcome you all for the inaugural function of the FDP on emerging trends in electronics, communication, and networking technologies, organized by the Department of Electronics and Communication Engineering, Sri Vidyaniketan Engineering College, Tirupati. We have gathered here for deliberating on this FDP. It provides a platform for academicians, researchers, industry participants, practitioners, and budding engineers to disseminate the most recent innovations, trends, concerns, along with the present day challenges, and also the solving approaches in the domain of electronics, communication, and networks. Moving forward, I would like to invite Dr. N. Giri sir, Professor and Head, Department of Electronics and Communication Engineering, to deliver the welcome note. Sir, Giri sir. Sir, HOD sir.
Okay. Very good evening to one and all. Respected Dean, Dr. P. Venkatramana, today's speaker and the chief guest, Swapna Rao, my dear participants and my dear colleagues of Sri Vidyaniketan Educational Institutions, I wholehearted welcome you all for the faculty development program on emerging trends in electronics, communication, and networking technologies during 25th to 29th October 2021. The main objective of this FDP is to understand novel issues and breakthroughs in latest innovations, trends, and challenges encountered in the field of electronics and communication, especially in the areas of fintronics, optoelectronics, network on chip, design and wireless sensor networks, and IoT. To gain practical approach with potential solutions to real-time problems by designing industry aspects in electronics domain. Devoted to fundamental theory, recent developments, and research outcomes addressing the real theoretical and practical aspects of engineering applications. My heartfelt thanks to all the speakers for their acceptance to be with us on this occasion. Once again, my warm welcome to all for the faculty development program on emerging trends in electronics, communication, and networking technologies organized by the Department of ECE, Sri Vidyaniketan Engineering College. Thank you, sir, for giving this opportunity.
Thank you, sir. Next, I request the Dean Academics, Dr. P.V. Ramana sir, to speak on this occasion. Ramana sir.
Okay, respected Swapnil and my dear colleagues, a pleasant evening to one and all. This is a one-week faculty development program on emerging trends, electronics, communication, and networking technology. Coming to this communication and networking technologies, lot of happenings is being taking place. If you see the digital, the cash flow today, most of this cash flow is becoming digital transactions, and the existing communications is being replaced with the artificial intelligence based, interactive based communications, and hybrid approaches in the communications, and most of this becomes a wireless mode, a background with a wired mode, and at the same time, it given an opportunity for the engineers to work on more in terms of the security or the requirements of the customer in terms of speed, in terms of features that is enabled in the communication with a secured mode as becoming a challenge for the engineers. And even the existing communications is being replaced, is being moderated with additional features. And many of these communication that takes place in any one of the category of networking or the mode of networking. And coming to the networking technologies, security is the highest issue today. And these networking technologies made the communication more cheaper. Today, thousands of people at one platform would be possible because of these networking technologies. Example, let us take this Zoom now. Right now, we have 47 members are on the platform. That is all because of the networking technologies that supports in communication has become the wireless is the emerging. Along with this, the hybrid approach and the AI and machine learning algorithms made this communication more smart and as well as helpful for the community. And security is one of the major challenge which will address in near future with the voice interactive based communication instead of doing all these transactions instead of by typing this PIN number. All this is a voice based, and this hybrid approaches makes the people to think in a different mode of the communication, which becoming the emerging trends. And fortunate that our people have planned in FDP on emerging trends in communication and networking technologies. I request the members to utilize this program and enhance the knowledge or awareness on that taking place in communication and networking technologies. I thank Ashok for the initiation he has taken to organize this event, and whoever involved here, I personally thank each and everyone on behalf of management, faculty and staff. I thank the participants and the experts for attending the program. Thank you very much for providing the opportunity. Thank you very much, Ashok.
Thank you very much, sir, for your concern, support and encouragement. Now, I invite the Vice Principal, Dr. T. Nageswara Prasad, sir, to share a few words. Sir. Giri sir. Sir, Giri sir, HOD sir. So due to some network issue, he quitted from here. Okay, he will join. He will join. That time he will convey something. Okay, this is Dr. N. Ashok Kumar, working as an associate professor in the Department of Electronics and Communication Engineering at Sri Vidyaniketan Engineering College, Tirupati. Myself, Dr. P. Geeta, we are the coordinators of this workshop. It's my pleasure to introduce our chief guest, who is going to deliver the today's session, Dr. Swapnil Pugate. Currently, he is working as an associate professor in the Department of Electrical Engineering, Indian Institute of Technology, Tirupati. He has completed his BTech in IIT Kanpur, MTech in MNNIT Allahabad, PhD in IIT Bombay. His areas of interest is spintronics, in particular acoustically driven magnetization dynamics, spin torque oscillators, and nanoscale devices. he have funded projects in SERB under EMEQ scheme, and he have 36 reputed journals in national and international level. Welcome you, sir. Now, I request that today's chief guest, Dr. Swapnil Bhuktare, to speak a few words on this FDP. Dr. Swapnil.
Hello.
Yes, Dr. Swapnil, welcome you. Welcome you,
Thank
sir.
you. Thank you, Dr. Ashok, for introducing me and giving me this opportunity. It's a wonderful thing that you are doing, you and Dr. Geeta, that you have organized this 1 week FDP program on the emerging trends in electronics, communication, and networking technologies. As Dr. Ramna, your dean, he has also pointed out how fast, how rapidly the technology that's progressing. And it's a very good thing that you've done this FDP where researchers or engineers, they're participating, and then there can be some discussion on these emerging trends or the emerging technologies which are coming and what are the challenges which are there. So yeah, I would like to thank you very much for taking this initiative, and again thank you for inviting me to this FDP and giving me this opportunity to share about my research work or my research field. Thank you very much.
Thanks for gracing the occasion, sir. It's our pleasure to have you here. Let's move on the session. Dr. Swapnil Bhuktare, sir, hand over to you. Your session continues, sir.
Okay, thank you,
Yeah,
Dr.
thank
Ashok.
you.
Can you see my video?
Yes, I will make a host to you. Wait,
Okay.
then only you can able to share.
Yeah, and I would like to share the screen
Yeah.
also. Or you can make me co-host actually,
Yeah.
host, because
Yeah,
I'm
I
also
will.
not sure about the I have made one alternative arrangement for the internet, but I'm also not sure. So yeah, you can
Okay.
make me a co-host.
Yeah, sure.
Yes.
I made it. Swapnil, I made it.
Yeah, thank you. Yeah, I'll share my screen. I hope you can see my screen.
Yes.
Okay, thank you. Thank you, Dr. Ashok. I think let's get started.
Yeah, your session starts now.
Yeah, okay, yeah, thank you. Thank you, Dr. Ashok. Good evening, everybody. Myself, Dr. Swapnil. I'm currently working as an assistant professor in the Department of Electrical Engineering at IIT Tirupati. Dr. Ashok has already given the introduction about me. So I think I'll now straight away go to the presentation. As you know, the topic of the presentation is spintonics. So I'll start with a brief overview of this presentation. Say what are the things that I will be discussing or will be going through in the next 1 hour. So I'll start first with why spintonics. Okay. Before talking about exactly what spintonics is, I'll first tell why spintonics, why we may need it. Okay, and then of course I'll talk about what spintronics is, what is this new emerging technology. Then I will talk about some of the flagship devices which have come out of this technology, the GMR or the TMR, the giant or the tunnel magnetoresistance devices. And then I'll talk about the applications. That's very important. We have it because it is giving us certain useful applications. Okay, and the ones that I'll be talking about: sensors, memory, how these devices can be used for memory or say logic operations. And then I'll talk about some other devices, say oscillators, which can be used as RF sources or detectors in the communication systems. And then I'll end with a future perspective about this field. What are the latest things which are happening and where I guess you have heard this name, Gordon Moore and the Moore's law. You have studied electronics, you probably know this, and that's the law about the scaling of the transistors. It's not as such a law that you study in physics, something like say Newton's laws. It was kind of a prophecy given by this gentleman, Gordon Moore. You see here, he was one of the founders of Intel. He made this prediction that the number of transistors on a given IC that will double approximately every 2 years. And you see here this graph, it shows the transistor count in a IC chip inside, ICs, the integrated circuits, the count of the transistors inside, and on the x-axis you see the years. See, probably in 1970s, you see there are probably 1,000 transistors inside the IC, and then their dimensions maybe of the order of millimeters or say few hundreds of micrometers. And then you see with time how that number has kept on increasing. If you see today, the state of the art, if you take the ICs, the device dimensions, they'll be of the order of few nanometers. And you see the transistor count, you'll have billions of such devices on a small IC, which may be of the size of say few millimeters or few centimeters at the max. See, that's how the technology has progressed. And I said, this has become possible with a continuous reduction in the dimension of these devices, say the transistors, because they are what are used in your say ICs, which drive your smartphones, your laptops, and there's something that has kind of revolutionized the way we live our modern lives. The scaling has continued throughout over, see the timeline, maybe from 1970s to almost say 2010s, 2020s. The dimensions have reached, as I said, probably few nanometers, 7 nanometer node that's already there. So, if you take say 1 nanometer, that's like a billionth of a meter, and it will have maybe 3 to 4 atoms. So we are having say tens of atoms. That's how small the devices have become. And how long is it going to continue? So we have 7 nanometer, they're pushing for 5 nanometer. The ultimate limit is like we'll reach the dimensions of atoms. Right. So, and it's expected that the strain, it's not like something that will continue forever. And with this continuous reduction in the device dimensions, there are other problems which are coming, like heat dissipation. And then there'll be some quantum mechanical effects, which will make a realization of those devices with such small dimensions very difficult. And therefore, there's hunt for alternative technologies. And one of the most promising options is spintronics. So now I'll talk about what spintronics is exactly. No, the conventional electronics that is based upon the charge of the electron. So you take your transistor device, you apply the gate voltage, electrons flow from source to drain. There's a movement of charge. That's how current moves. Okay, so say you take other devices like memory or logic. Sometimes say we take the voltage signals, or say the presence or absence of charge as our logic values, say zeros and ones. The spintronics, it's the spin-based electronics. It uses the spin property of the electron, and using that property, it wants to design new devices which can show improved performance or functionality, say faster devices or devices which will consume very less power. Okay, so it's basically spin-based electronics. Electronics which works on the spin property of the electron. Okay, and as these days we are fond of fancy terms. So the spin-based electronics or spin electronics, these terms which give rise to this spintronics word. Okay, let me quickly talk about what spin exactly is. Spin is a quantum mechanical property. It's a basic fundamental property of the electron. We know, say, electrons have got a mass. It's like if you take rest electrons, it's like 9.1 into 10 to the power minus 31 kg. They also have got a charge minus 1.6 into 10 to the power minus 19 coulomb. So these are like the fundamental properties of the electron. The same way, spin is also a property of the electron. It's basically a form of angular momentum that's also associated with the magnetic field. Classically, I hope you have seen this analogy. We take a spinning ball, and depending upon, say, it rotates in the clockwise or the anti-clockwise direction, we say it's like the upspin or the downspin. That's a very classical, or say a crude analogy for the spin of the electron. In reality, it's a little more complex thing. It's not like the electron is like physically revolving around some axis. It's a form of angular momentum, that's true, but it's a quantum mechanical property. And how yeah. So I was talking about the discovery of spin. There was this classic experiment done by Stern and Gerlach in 1925, is what you see here. They had some oven which would emit silver atoms, and those silver atoms they were made to pass through a non-homogeneous magnetic field, and there was a screen here which detected these silver atoms. What they found was two clear distinct spots on the screen. If you see the electron, I said they have spin. It's a form of angular momentum which is related to the magnetic field. It turns out that every electron behaves like a tiny magnet with some magnetic moment that's associated with it, that's related to this spin property. Okay, so now in general, no, if you take most of the atoms, there are these electrons inside, and then the magnetic moment, say due to upspin electron, that gets cancelled by the moment due to the downspin electron, and so there's no net magnetization. But then there are some atoms, say where you can have a net magnetic moment, and then there are materials which are ferromagnetic materials like iron, cobalt, or nickel, which have strong magnetization. Okay, so it turns out, as I said, so if you take the silver atom, okay, so there, let's say it has that one extra electron that's there, which gives rise to the net magnetic moment, and as they pass through the inhomogeneous magnetic field, they experience the force, and then due to that, say they're scattered in the up direction or the down direction. Now, if you pass, say, classical magnets through this apparatus here, you expect a continuous distribution, because the classical magnets, say the magnetizations can be oriented in all possible directions, and therefore you expect a continuous distribution. But as I said, with spin, it's little more mysterious. It shows only two distinct spots. So if you measure this angular momentum, it shows that it has got only these two values. So it's what we call, say in crude language, maybe upspin or the downspin. Okay, and that you see there's something that's like you can say quantized. The angular momentum is quantized. If you see the way we denote it, so it's like the plus half or the minus half, the spin quantum number. And if you talk about the exact values, it will be like plus minus h bar divided by 2. Okay. And then from these experiments, one can actually find out what will be the, say, the magnetic moment of the electron. Okay. So that was the experiment which sort of told us the existence of spin, and it was also very important in laying the foundations of quantum mechanics. Because there, if you have studied it, say if you take the hydrogen atom, we know the energy levels are quantized. Okay, so that quantization is something that's inherent or inbuilt into quantum mechanics. And then you see here, the same goes for spin. Okay, I guess talked a lot about physics related aspects. Let me come to the electronics part now. And what I will do is I will talk now about the discovery of the giant magnetoresistance effect. Magnetoresistance is a general term that is used to define, say, change in the electrical resistance of a material in the presence of magnetic field. Okay, so if you apply the magnetic field, there may be some change in the resistance of the material. It depends upon the magnitude as well as say, the direction of the applied magnetic field. GMR, the giant magnetoresistance, it was discovered by Professor Furt and Professor Grunberg in 1988. The results from one of their papers, they have been shown here. What they had was alternating layers of ferromagnetic materials separated by some non-magnetic conducting metals. They used this FeCr layers. Fe is iron, which is a ferromagnetic material, and then Cr is chromium, that's a non-magnetic material. So they had they had a device which had this alternating layers of Fe and Cr, and then they measured the resistance of this device as a function of magnetic field. So you see here in this graph, what you see is this resistance. It's scaled with respect to the maximum resistance, and see it has been measured as a function of the magnetic field. At zero magnetic field, you see the resistance is maximum, and then as you increase the magnetic field in either direction, the resistance goes down. And these results, they are shown for different say different layers with different thicknesses of the chrome material. Okay. So probably I'll not talk about this aspect, how it changes with the thickness of the chromium. That involves something called the interlayer exchange coupling. The basic idea I want to illustrate is the change in the resistance in the with the magnetic field. And the next slide, I have a good animation which will explain this phenomena. So what happens is the scattering or the resistance that the electrons face that depend upon the relative orientation of their spin to the magnetization direction. Let me show you this animation. I hope you can see it. I hope you are able to see the video, Dr. Ashok.
Yeah, yes, sir. We can
Yeah.
able to see.
Yeah, okay, okay. Yeah, I hope now the idea is clear. See, if the spin of the electron points in the direction of the magnetization, the resistance that it will face will be small. If the magnetization direction is opposite to the direction of the spin of the electron, then it will face more resistance, or say there will be more scattering, and that way the resistance will be more. Okay, and you see now how, by changing the magnetic field, say we can change the magnetization direction of the ferromagnetic material, and that way the resistance can be changed. Okay, so if you see, if they are, if both the magnets they point in the same direction, that's their parallel alignment, the resistance will be small. If they point in the opposite direction, the resistance will be large. That's the basic principle behind, say, the working of these magnetoresistance devices. Okay, so what Professor Firth and Gunberg, they had FECR, this layer structures. With time, people develop devices called spin walls. They basically had two ferromagnetic materials separated by some spacer material. And that is the basic structure is what has been shown here. You see the two ferromagnets, say FM1 and FM2, and they are separated by some material called as spacer. And in general, say this spacer, it can be some conducting material like chromium, copper, or it can be some insulating material like, say, aluminum oxide or magnesium oxide. What happens is the way they make this, you see, let's say the ferromagnet one, the magnetization of this is relatively fixed. It's difficult to change. The ferromagnet 2, the magnetization can be changed relatively easily. So the ferromagnet 1, that's what is called as, say, the pinned layer, the magnetization remains almost fixed. The ferromagnet 2 is what is called as the free layer. The magnetization can be changed easily. Okay. And now, say you pass current through this device. So if both these ferromagnets, FM1 and FM2, if they point in the same direction, the resistance will be small. If they point in the opposite direction, the resistance will be large. One can understand this further with a very crude optical analogy involving polarizers. The situation is shown here. Say you have this polarizer. Now I'm talking about optics. Okay, I hope you know this. The polarizer, we consider, say, light as electromagnetic waves with electric and magnetic fields, and then the direction of the electric field is what we associate with the polarization. And then we have certain materials, say polarizers. If you pass a light through it, they'll polarize it, or say they will allow only light of that particular polarization to pass through. Okay, so let's say you have this polarizer here, and I have one more polarizer here that is oriented at an angle theta with respect to the first one. The second polarizer is what I call as analyzer. And now if you pass light through it, you know the transmission will be proportional to cos square theta. This is what is referred to as the Malus law. Okay, if say the theta is 0, if they are like parallel, you'll have maximum transmission. If this theta is 90 degree, you rotate it, you place it at right angles with respect to the first one, the transmission will be minimum, or it will be 0. Okay, so this is something all of us know. It's called the Malus law. You see, now this device, say the spin wall, it works in more or less the similar way. See, now you are passing current through it. This pinned layer, it sort of acts like a polarizer. As you pass electrons through it, their spin tends to get polarized along this direction, the magnetization direction of the pinned layer. So this acts like a polarizer, and then these electrons, this case, they sort of become spin polarized. Here, you had light waves. Okay, so here we are talking about, say, electrons, they become spin polarized. So here polarization, refers to spin. Okay, here in the optics, it referred to say the direction of the electric field. Okay, so the electrons get spin polarized, and now you have this free layer here. This sort of acts like analyzer. Say if the incoming electrons, if their spin is in the same direction as that of the magnetization of this free layer, the resistance will be minimum, so they can pass easily. It's like, say, your transmission will be maximum. You'll have less resistance. Say if this this magnetization, it points in the opposite direction, then the transmission will be minimum. You'll have a maximum resistance. Okay, so that's this simple analogy. Okay, as I said, this very crude. You may have noticed a simple difference straight away. Here, the dependence we say is like cos square theta. So this theta should be 90 degree in case of, say, this optical polarizer, so that the transmission will be minimum. This case, if you talk about spin walls, here it so happens that the theta should be 180 degree. Okay, you see this, the parallel arrangement, they point in the same direction, and here they should be anti-parallel. See, so it should be pointing in the other direction, so that you will have a minimum transmission, or say a maximum resistance. One can understand it using the simple resistor model also, which has been shown here. Say you have these two ferromagnets, and then say the spacer is what I'm calling as the channel. Say if you see, let's say the first case where we have, say, the parallel arrangement. Okay, so let's say you have this upspin electrons here, which are in majority, say this as well as this, and now you have this channel. So this channel, as I said, this is a non-magnetic material. So the channel will have, say, equal number of upspin and the downspin electrons. And it usually will not differentiate between the upspin and the downspin electrons. It's these ferromagnetic materials which have this distinction, which will make this distinction. Okay. So now let's say the electrons are coming from this ferromagnet into this channel. This channel now, say, we can divide it into two parts. One for the movement of upspin electrons, and one, say, for the movement of downspin electrons. So you see, let's say this, the red one that corresponds to, say, the upspin channel, the blue one that corresponds to your downspin channel. And that's what in normal materials we can do that, because they behave equally to the upspin as well as the downspin electrons. So if you remember, say if you studied device physics, what we do is we calculate, say, properties like conductance or density of states due to one type of electrons, and then we simply multiply it by 2, because we know that it's not like just one electron that's there. They can be of 2 types, say, to consider it in a simple way, say upspin and downspin. Okay, so now if you see here, for example, say these upspin electrons, they enter into the upspin channel, the resistance will be small, say that's smaller. Now here again they exit into the ferromagnet whose spin is pointing upwards. Okay, so again the resistance will be small. Say the channel, the resistance is RCH. Okay. Now, if you take this case, let's say if the upspin electrons, they want to enter into a downspin channel, the resistance will be large. That's what this capital R is. RCH is again the resistance of the channel. And again, let's say here you have a downspin channel. From there, they are entering into this ferromagnet which points up. So the resistance will be large, capital R. That will be for the parallel case. For the anti-parallel case, the situation is shown here. So this one points upwards, and then this magnet, the magnetization, say it points downwards. Now, say this upspin electron enters into the upspin channel, resistance will be small. Now here, at the other ferromagnet, it will go from the upspin channel to this magnet, which is pointing downwards. So the resistance will be large. And same way you can see this case. And now you see the simple model tells us that the resistance of this device will be different for the parallel or the anti-parallel configurations. You can write down very easily what will be the resistance in the parallel or the anti-parallel cases. And from that, you can find out the magnetoresistance. The way this magnetoresistance is defined is something like this: RAP, that's the resistance in the anti-parallel state, minus RP, the resistance in the parallel state, divided by RP. And then sometimes it's multiplied by 100, and people talk about the magnetoresistance in terms of percentages. So that was the spin wall, say, where mostly what they do is this spacer material that's like a conducting metal, like something like chromium or copper. Now, for practical applications, we require large magnetoresistance, and people found out that if you replace that conducting metal with some insulating material like aluminum oxide or magnesium oxide, the magnetoresistance that one gets, that can be very large. Okay, that's what has been shown here. So you have these two ferromagnets, F1 and F2, and then they are separated in this case by some insulating material. This case, because you have this what is called as the tunnel barrier. Okay, and see, now this is insulating material, so the resistance will be large. And then it turns out using them, one can get larger magnetoresistance also. Okay, probably I'll not be going into this density of states diagram. What it shows is, if you have, say, these ferromagnetic materials, it shows the energy levels corresponding to the upspin and, say, the downspin electrons, or say the magnets which are pointing in up or the down direction. Okay. Typical device structure is what has been shown here. I said you'll have only two ferromagnets separated by some spacer material. But if you see in reality, the structure tends to be a bit more complicated. You see, I talked about the pinned layer and the free layer. Right, pinned layer, the magnetization is relatively fixed. It's difficult to change, and to do that, they use something called the exchange coupling. They have this anti-ferromagnetic materials which they put here. Okay, and then there will be sticking layers, the contact layers. So there'll be a stack of thin film materials like this. Okay, and then if you see, let's say typically you measure, say, the resistance of this device as a function of magnetic field. This is how it may look like. You see, let's say if you have parallel arrangement, the resistance will be small. If you have anti-parallel arrangement, the resistance will be large. Okay, so what you are doing is, say, you're sweeping the magnetic field. So this pinned layer, the magnetization, it almost remains the same. It's the magnetization of the free layer that gets changed. Okay, so typically, let's say you see here, maybe you need like probably 100 overstates magnetic field, say, to change the free layer magnetization. Say, if you take, let's say, this case, say this is your pin layer, this is your free layer. Now let's say you apply magnetic field in this direction, maybe say 100 or 200 OE overstate you apply, and what it will do is it will change this magnetization from this direction to, say, the other direction. And in this process, what happens is the magnetization of the pinned layer that almost remains the same. That's why I said you need to design it properly. such that it's only the free layer magnetization that flips, that changes. The pin layer magnetization remains almost the same. Okay. And now you see you have this device where the resistance shows two states: low resistance if they point in the same direction, or high resistance if they point in the opposite direction. And you can see their immediate applications in terms of sensors. You can use them to sense the magnetic field. The resistance is changing with the magnetic field. That's the obvious thing. And the other major impact of this was on the read heads which were there in the hard disk drives. This made a revolutionary change in the hard disk drive technology, the GMR read heads, and this impact was recognized by a Nobel Prize in Physics in 2007. Professor Furt and Grunberg, they were awarded the Nobel Prize in Physics in 2007 for this discovery of the GMR effect. What you see here is, say, this is the structure of, say, your hard disk drive. So you see here this blue one, that's like your disk. It will have, say, those magnetic materials. There'll be those thin regions of magnetic materials, and the information is stored in the orientation of the magnetization. You see here, for example, probably you can see it here. You see, let's say you have this tiny region, say the magnetization points in this direction. You have this other tiny region, say the magnetization points in this direction. Okay, so such tiny regions will be there on, say, this disk. Okay, and it's like they're arranged in the form of tracks, and that's what they call it. And it is in these tiny magnetic regions where the information is stored. So if it points in this direction, maybe you call it 0. If it points in this direction, say you call it 1. And that's how the information is stored, in this digital. It's stored in terms of binary, say the 0 and the 1. So you are using, say, the orientation of the magnetization to store the information. And you see now there's a disk, and then on top of it, you see there's the structure with actuator, and then this read and write head. And you see this disk, it can rotate at speeds of, I think, a few thousands of revolutions per minute. And then there'll be this head on top of it, has got some actuator. See here, the write and the read operation, it has been shown here. So the writing is done inductively. So they have some coil kind of arrangement. They pass current through it, and then the current creates the oversted magnetic field. And with that magnetic field, say they can write. Okay, and then they'll use this GMR read head sensor here to detect, say, what is the orientation of this magnet, this tiny magnetic region that's there. Okay, and as I said, this has really revolutionized the hard disk drive technology. These days, you see, in very tiny spaces, we can store, gigabytes of information. That's this immediate application which was there. The other application is in terms of memory devices. For memory devices, there are these 3 important things which you should be able to do. You should be able to read what is stored there. If you want to modify, you should be able to write. And depending upon how you want it, volatile or non-volatile memories, that data, it should be stored there. Okay, so These are the three important things when it comes to memory devices: how you can read, how you can write, and how the data is stored. If you see, we talked about these devices as spin walls or magnetic tunnel junctions. Right? We said the resistance can be low or high. Okay, so in those states, you can basically store the information. The actual arrangement is what has been shown here. You see, you have this magnetic tunnel junction device here, and then this one transistor, and then this bit line, word line. Now, if you want to read it, what you can do is you can pass current to the MTJ device, and you can read the resistance. So if it's low, you call it 0. If it's high, you call it 1. That's the way you can read it. If you want to write it, what you can do is you may need to change the orientation of the relay. See here. Say if the relay was pointing here, that's the parallel case. Say maybe you're calling it 0. You want to now write 1. So what you do is you apply magnetic field, and then you change the orientation of the relay. So you change it from here to here. And that way, say now you have made the anti-parallel arrangement, and say now you have written 1. So that's how say you can write the information. And the earlier technology, what they would do is, again, they use some current carrying conductors. You see here, there's a conductor which carries current, and then it will produce this oversted magnetic field, with which say one can change the magnetization of the field. Okay, and actually the way they would do is they had this, say, one current carrying conductor, and then there's one more, say probably this bit line. Through this also they would pass current. So the arrangement and the design is made such that if the current is passed through both these wires, so this bit line and you have say one more wire here, then only say enough magnetic field will be produced so that you can change the field magnetization. Okay, because say these bit lines, there may be other devices here, so it goes through a lot of devices. Okay, so you need to select one particular device, and that's how say these bit lines or word lines you use them. Okay, so that arrangement needs to be done. Okay. And then, as I said, what you do is say you want to write it, say you change the orientation, say from one direction to the another direction. And then if you see in terms of the energies, see these are what you can say the stable states of the magnetization. Say the free layer magnetization, say if it points in this direction or if it points in the other direction. These are like say the stable states. Okay, so that also depends upon something called the anisotropy, which probably I won't be going into. Okay, but you can see these are like stable states, and then say you want to go from one state to the other state, you need this magnetic field or there's some energy that you need to provide. Okay, so in terms of the energy, that's what has been shown here. See this kind of thing. So let's say these two positions you see here, they sort of represent the energy minima. It sort of indicates that let's say these two positions that you have, or say these two orientations you have, they're stable. And then if you want to go from one to the other, need some energy, right? That's what this barrier you see here, that's what it presents. Okay, and then I know if you want to do these designs properly, you also need to take into account say the thermal fluctuations. Because see, if you have operating these devices at room temperature, okay, so you don't want, let's say, this the magnetizations to flip because of thermal energy. So you also need to consider what is this energy barrier and what is the stability that you are going to get there. Okay, so this the other major application, the magnetic random access memory. And the way in the early technologies they would do the writing, they would do it with the help of magnetic fields. Now with time again, no, you need to scale these devices, right? You need to pack more and more such devices into a given area, so that, you know, say instead of having say 1 megabytes, you can get 10 megabytes or 100 megabytes of memory. So it so happened with these configurations or this way of writing, if you scale it down, if you reduce the dimensions to switch this 3-layer magnetization, it required larger currents. And then that then produced the heating issues and all. So people then know they explored the alternative technologies, and the one that's currently used is this technology of spin transfer torque. It's also abbreviated as STT. It was proposed by Slonczewski and Berger in 1991 in magnetic multi-layer devices. The situation is shown here. This something similar to say your spin wall or MTJ device. So you have say 2 ferromagnets separated by some spacer material, and say this ferromagnet 1, that's your pin layer. So the ferromagnet 2, that's like your free layer. Now say you are passing electric current through this device. Now electrons are moving. Now the electrons, they enter into the first ferromagnetic material. As I said, these ferromagnets, they sort of act like polarizers. So what they do is they will polarize the spins of the incoming electrons. You see here, say these electrons which are incoming, their spins may be pointing in random directions because they are coming out of, say, your battery. So their spins may be randomized in all directions. Now, as they enter into the ferromagnet 1, their spin will get polarized. So they'll point in the direction of the magnetization of ferromagnet 1. And then you see in the spacer, they're all polarized in the direction of the first ferromagnet's magnetization. And now these electrons, they enter into the second ferromagnet. Say the second ferromagnet, it is pointing in some other direction. That's indicated by, say, this black arrow. Now you see these electrons, their spins, they are in one direction. And now this ferromagnet 2, the spin is in another direction. So what happens is there can be exchange of angular momentum. As I said at the beginning, spin is like a form of angular momentum. So these electrons which are incoming, so they would like to see the spin of the second ferromagnet, or say the magnetization of it, also in the same direction. So they can exert a torque on the magnetization of the second ferromagnet, and they would also like to align it in their own direction. And this phenomena, this is what is called as the spin transfer torque. The electrons, they are carrying with them this angular momentum in the form of spin, and when they enter into the second ferromagnet, they would like to see the magnetization of the second ferromagnet also in the same direction. To do that, they can exert torque, and that is what is referred to as the spin transfer torque. And you see, if you have enough number of electrons, let's say with spins pointing in this direction, if they come here, they can transfer enough angular momentum, and then they can, change the magnetization direction of the second ferromagnet. They can switch it, they can move it in the other direction, or if you use it properly, they can also cause this magnetization to oscillate. Okay. And this is what is actually governed by the LLGS equation, the Landau, Lifshitz, Gilbert, Slonczewski equation. It tells us how the magnetization will change with time. See this equation, there's this m hat that's like the unit vector in the direction of the magnetization. Okay, see ferromagnet 1, say the magnetization is in this direction. Ferromagnet 2, say the magnetization is in this direction. So m hat is like a unit vector in these directions. Okay, so how it will change with time, that's what this equation tells us. There's the LLGS equation, the dm hat by dt, the way how m hat changes with respect to time is this minus gamma 0 into m hat cross h effective. Gamma 0 is a constant, which is called the gyromagnetic ratio, depends upon the material. Then H effective is the effective magnetic field. So you may have applied some external magnetic fields, and then sometimes there may be some internal fields due to anisotropies and all. Okay, so this is the first term. This is what is called as the precession term. If you solve this equation with just the first term, it will tell you that m hat will precess around the effective field H, and that is the situation shown here. Say you have this effective field, say H0, you apply in this Z direction, say, so the magnetization would like to precess around that. But then the precessions, they can't continue forever. You'll always have some natural damping that will be present in the system. So the second term is what tells us the damping. Alpha is the damping constant, alpha times m cross dm by dt. So what this damping would like to do is, it would like, let's say this is the magnetic field, say electron is precessing around it. So the damping would like to reduce these amplitudes of precession, and it would finally like to align this m hat in the direction of this magnetic field. Okay. So that is the damping term. And now you have this spin transfer torque effect, and that you can include like this: m cross is by qns cross m. Is sort of represents the spin current. So we are saying, let's say we are talking about the charge current. Okay, so it depends upon the polarization. As I said, you have the electrons which are coming, they are passing through ferromagnet 1, and then they are getting polarized. Okay, so this is will be, let's say, how many of them they are getting polarized. So that polarization factor times your DC current. Ns is the total number of spins which are coming. Okay, and now you see, using this term, what you can do is you can switch the m hat, the magnetization, or if you adjust these parameters properly, say your magnetic field and your current, what you can do is you can cancel this damping, and you can make the magnetization to precess continuous. And that precision is used in the spin torque oscillators. That's what I'll talk about that soon. Okay. Before that, there's one more kind of device that I want to talk, and that's the field effect transistors using the spin of the electrons. We know the normal MOSFETs, how they work. We have source and the drain, and there's this gate terminal. We apply a certain voltage at the gate, and by that gate voltage, we control the electron flow between the source and the drain terminals. The spin FET, if you see the original design, it was proposed by Datta and Das in 1991. It has been shown here. Here, what you have is the source and the drain. They are made up of ferromagnetic materials. Okay. You see here, let's say this is a source. Say it points in this direction, and say the drain again points in this direction. So let's say you have parallel arrangement. Now you pass electrons through this. Okay. So let's say the electrons are coming, and now what you do is you apply a certain magnetic field. The magnetic field, as we saw, what it does is it would like to resist the electron spin. So let's say now these electrons, when they exit out of this, say the left contact or say your source terminal, the spin, it will point in this direction. Now you applied the magnetic field. So as they travel through, they go from source to drain, the spin, it tends to persist. Okay. And then now you see, let's say here, two situations have been shown here. The first one, say you rotate the spins by 180 degree. So that let's say when the electrons, they come near, say your drain contact, the spins of them, they point in this direction. Now you see the drain, it's pointing in this direction, the magnetization, and the upcoming electron, the spin is in the opposite direction. And now what will happen is due to this difference, this upcoming electron, it will face a large resistance while it enters into this drain terminal or as it travels. And this way, you see now the resistance between the source and the drain, that will be high. If you adjust your magnetic field such that, say the electrons, they complete a rotation of 2 pi, say at this the second case, say they also point in the same direction as that of the drain contact. This case, the resistance will be low. So this will be, so you'll have high current. So this will be like your on state and this will be like your off state. So this way you can realize even the field effect transistors in spintronics. The only little complication that's there is, again, they don't apply the magnetic fields directly. That's a little difficult to do. So what they use is something called the spin orbit coupling phenomenon. What they actually do is, see here you have the gate electrode. They apply the electric field. So they'll apply certain voltage at the gate. And because of this phenomena called spin orbit coupling, this electric field effectively behaves like a magnetic field for these electrons. And again, for that, you need to choose certain materials with large spin orbit coupling or certain semiconductors. Maybe if you take, say, silicon, the spin orbit coupling may be low. You may have to go to some other 3-5 compound semiconductors, or maybe people also use, say, 2DG gas kind of channels here, so that there's a large spin orbit coupling. And then even instead of resorting to magnetic fields, you can control everything with electric fields. That's this spin fed device. Okay. Then I already talked about the MRAM devices, and I said the earlier technology, what they would do is they would change the 3-layer magnetization using magnetic fields. If you remember, I talked about it here. So they would change the 3-layer magnetization using the magnetic field. And as I told you, this is not good if you want to scale these devices. Okay, so then people started using the spin transfer torque technology to switch the magnetization of the 3-layer. That's also makes the design and the fabrication very easy. The schematic is what has been shown here. So you have this bit line, word line, and now see, you don't need extra current carrying conductors. You're not using overstate field to switch the magnetization. You want to switch the magnetization, you simply pass electric current to the device itself. And that current itself, due to the spin transfer torque phenomena, you can use to change the 3-layer magnetization. And that's again something that has been shown here. So how you can go from parallel to anti-parallel, or say anti-parallel to the parallel arrangement. Okay. Dr. Ashok, how much time I have still?
Hello? You will take a few more minutes, sir. Up to 7:40 you will take.
Okay, probably, yeah, I'll try to wind up now in 5-10 minutes.
Yeah, sure.
Yeah. So this makes the design and the fabrication process very easy if you use the STT technology. And these days now people use something called the PMA materials, the perpendicular magnetic anisotropy materials. We said, till now we are talking about devices where, say, the magnetization, they lie in plane. Now, these are the materials where the magnetization lie out of plane. And it turns out that these materials, the magnetization tends to be more uniform, and then they are less susceptible to noise. We said, the magnetization should not flip because of thermal noise. Like if it does that, then your storage, the data that you have stored there, that will change automatically, and that's something you don't want. So that's again one line of research where people work. Then there are these tiny oscillators that you can make out of the magnetic tunnel junction devices. If you remember, I talked about the STT, and then I said that STT, you can use it to switch the magnetization or drive it into continuous oscillations. Okay, and say if the magnetization, you drive it into continuous oscillations, now the resistance depends upon the relative orientation between the free and the pinned layer. The pinned layer, the magnetization orientation is the same. Say the free layer, the orientation is changing continuously. So what will happen is the resistance of the device, that will also change continuously. Okay, and then you can get oscillatory voltage across the device, and that's how you can realize what are called the spin torque oscillators. The advantage is the size of this device, that's really very small. If you see, let's say the magnetic tunnel junction device, the state of the art, probably the cross-sectional area maybe like few tens of nanometers, and then the thicknesses of these layers, that will be like very small. So these are extremely small devices. Then they can be tuned, say the frequency of the oscillations, one can change that with the help of electric currents or magnetic fields, and then they're compatible with the silicon processing technology. The existing VLSI technology that's there, the same one can use to make these devices with very few modifications. And then they're very useful as RF sources or detectors, and maybe used in communication systems. Okay. There are certain issues with them, like the output powers tend to be low, and then the line widths of the oscillations, they're finite, so the quality factors may be a little low. So people are working on techniques like locking and synchronization to address these issues. And then recently there's this other technology that has come, that's the spin orbit torque. Here what you do is you put let's say this magnetic tunnel junction device on top of some heavy metal like platinum or tantalum, and these heavy metals, if you pass charge current through them, they'll convert it into spin current, and then that spin current you can use to manipulate the magnetization of the field. So that's the latest technology, and using this again, say people are trying to make MRAM. They have again certain advantages over your STT MRAM. The power consumption will go down drastically. the switching will happen very rapidly. Okay, so that's the how, let's say, the things they are. And now I just would like to give a future perspective on this, and I would like to finish it off. I talked about the hard disk drives. If you see, with the advent of these GMR technologies, see, we can store a lot of data in a very tiny volume. And I talked about MRAM. There was this first 4 MB MRAM by Freescale in 2006. Now there's this company called Everspin, which is producing STT MRAMs, where you can store even up to 1 GB. And even large players like Intel or IBM, they're also investing heavily in this field. For, say, these MRAMs. And then now see, you must have noticed in spintronics, you would basically like to manipulate the magnetization of the materials. People are exploring electric fields to do that. And then there are other novel applications like, say, even neuromorphic computing or machine learning for AI kind of applications that can also be done with spintronic devices. There are people who are working on it. Then there are a lot of other applications. Spins, they can be used as qubits, which are like the basic building blocks of quantum computers. So people also, try to use them for quantum computing applications. Yeah, with this, I guess I'll stop here. Yeah, I guess I took some more time, probably. I actually wanted to like go a little slowly and explain a few things more properly, because we're limited by the time. It was only 1 hour duration. Covering such a huge topic in this 1 hour really was a difficult task, maybe for me, not that experienced. Yeah, I hope at least a few things you're able to understand and appreciate. Okay. Yeah, Dr. Ashok?
Yeah, yes, sir.
Yeah, probably we can take some questions now.
Yeah. Any queries from participant side? Any queries?
Yeah, just one query there was there in the chat box.
Yeah.
That's about they're asking about NMR.
Yeah, yes, sir.
Yeah, so NMR is like a magnetic resonance kind of thing. That's again something related to your ferromagnetic materials and how you do the magnetic resonance. Okay, so you can say it's like a part of it. Okay, so that's what you have to say, the similar ideas or similar concepts. That's what I use. Say you take your MRI, magnetic resonance image, or those kind of technologies also. Okay, so they use probably the ideas are similar, but I would say that's like a small part of this large field of what you can call, say, nanomagnetism and spintronics. Okay, so you use magnets and for, say, different applications. That's, they call it sometimes a nanomagnetism and spintronics.
Sir, here
Hello, Professor. Hello.
Sir.
I'm audible?
Yes, sir. Yeah, please ask one by one.
Yes. Yeah, sir. Thank you for this nice presentation, Professor. I have one question that you have shown that this nano FET is based on spintronics. So, what would be the substrate on which it will be that material will be deposited?
You are saying the spin FETs?
Yes, spin FET.
Yeah.
And
so,
what would be the voltage level?
Yeah. So these substrates, as I said, you need materials with large spin orbit couplings. Okay, so maybe there are some 3-5 kind of semiconductors. I guess indium arsenide and all those people are exploring. Okay, so
so this magnetoresistive material will be deposited on this on that 3-5 compound, and then it will act as a FET.
Yeah, so you see the basic, so this channel will be like some semiconducting channel. So if you take transistor, see, you'll have the source and the drain contacts, then there'll be this channel, and then say you'll have this gate contact, and using the gate, you control the flow between the source and the drain. Right. So here, let's say the channel will be this semiconducting material, but not maybe not silicon, like some other materials, some 3-5 or compound semiconductors, which have large spin orbit coupling.
Okay. And the
Okay.
voltage level that we have to provide on the gate and on the drain side.
The
That
voltage
level will be normal like a FIT, or it below that voltage.
I would say probably roughly of the same order.
Same order. Okay. Okay.
Yes. Yes.
Okay. Thank you.
Hello.
Yeah. Yes. Yes, please.
Yeah, I cannot hear any other questions.
Yeah. Any other questions from participant side? Participants, please.
Sir, it's a very nice presentation, sir.
Thank you. Thank you.
Yeah, sir, this is HOD, sir, Dr. N. Girish, sir. Dr. Swapnil?
Yes. Yes.
This
Yes.
is Dr. N. Girish, sir. He's HOD, sir.
Yeah. Yes. Yes.
Head of the
Girish, sir.
department, Sri Vidyaniketan College, sir.
Yes. Yes.
Sir, I am interested in biomedical. That's why I asked the question is because the spin is there in the NMR. So here also that rotation due to the spin rotations, so the alignments will be changed. So for that, I asked that question regarding the
Yes.
whether the spinning is there in spin like similar the concept of NMR and MRI.
Yes. Yes. Yeah. So the technology almost, I see here also, people talk about the ferromagnetic resonance and all, right? Yeah. So because see what we use there is like the say electromagnetic signals coming from the human bodies. We would like to process them and do certain diagnosis and all.
Yes.
Right? Yes.
Sir, here you are given example. One is force for measurement. The force torque measurement is given example.
Yes.
So, what is the minimum torque can be measurable, sir? Here, the spin transfer torque system.
Okay. This case.
Yes, sir.
Yeah. So this torque now you see it can be given by, let's say, this kind of expression. Okay, so this torque it depends upon, see what is the current that you are passing through. So see, with current you are having these electrons, and it's these electrons which are like exerting the torque.
Okay.
Okay, and it depends like how much current you are passing, how many electrons you are having, and then let's say if you take, let's say, the second ferromagnet, say how large this second ferromagnet is. See, if this second ferromagnet it is very large, then you need at least, see, it will have then so many electrons whose magnetization you want to change. So you want, say, this second ferromagnet to be like very thin. So that you can have sufficient torque which can say switch it, or which can drive it into continuous oscillation.
Okay. Okay,
And
sir.
these devices, if you see, the dimensions will be like really very small. Say if you take the cross-sectional area, maybe say few tens of nanometers by tens of nanometers, that will be like cross-sectional area. So probably say 20 nanometer cross 30 nanometer, say 50 nanometer cross 100 nanometer, something like that. That will be, say, the cross-sectional area, and then the thickness again that will be very small. Say few nanometers.
Sir, this is still research area. They are already implemented, sir.
This is already implemented. The STT, as I said, the MRAM based on STT, that's already there in the market.
Okay, sir. Thank you.
So this is already done. Now what people are doing is they're working on SOT. There's the spin transfer torque, STT. Now they're exploring SOT, the spin orbit torques.
Okay.
To say reduce the power consumption further, or say switch it faster.
Okay, thank you, sir. Thank you.
Thank you. Thank you.
Yeah, Dr. Swapnil. So
Yes.
can you give some ideas about industry aspect view and research aspect view, who are doing research in this area or who are going through this area?
Yeah. So I'll
Industry
say,
aspect view and tool aspect view.
yeah, I said here probably I mentioned like where exactly the field is going. So if you see right now, the industry that I've mentioned this exclusive company that's there, Everspin, who has already started the commercial production of 1 GB STT MRAM. Okay, and then these MRAMs say they're likely to probably replace the current maybe the flash memories that we have there. These memories, if you see, they are like non-volatile. Okay, so the information once you put it there, that will remain there. Okay, so these are like your non-volatile memories likely to replace your flash memories. They're like highly they're giving a tough competition, you can say, to the flash memories. They still there's a scope for improvement. As I said, now earlier say they would do the switching with the magnetic field, then they had this STT technology, then now they're exploring the SOT technology. Soon it's likely that SOT based MRAMs may come into the market, and then the next generation will be, let's say, where this the another technology, that's the electric field control. So first one was STT, the next generation is the SOT, and then they're looking for electric field control, which will further reduce the power consumption. So that's where say people are working right now, say how to control it using the electric fields. Okay, and then this now I guess these days you're hearing a lot about this boom in machine learning, artificial intelligence. So there's a lot of scope for this research and application also. Say you can use these devices for neuromorphic computing application. So this research is going on where say people have shown say the devices like magnetic tunnel junctions for pattern recognition and machine learning. Okay, that's like the hardware implementation of say the machine learning processes. How you can do say like pattern recognition, how it can be done using magnetic tunnel junction or say the spintronic devices. So that's again a very hot upcoming area where people are like doing the research. And then I haven't actually talked about these things, the qubits and the quantum computing applications. They involve a lot of physics, but again now this even our government these days is putting a lot of emphasis on quantum technologies. If you would have seen or heard in the news, there's a lot of emphasis that's going on quantum technologies. That's what the government or even the people feel. They are the futuristic technologies, not just say in terms of memory or logic. Even we have say quantum cryptography or quantum communication. So a lot of these quantum technologies they're expected to play a key role in your say futuristic devices or applications. So this again something that see a lot of research is going on, and yeah, people are looking for say commercial products, like even as I said quantum cryptography. Say I guess sir talked about security aspects.
Cyber security lo part. Unmute lo unnava.
Hello.
Yeah, yes, sir.
Yeah. So sir talked about this thing, right? The security aspects, right? So
Yes,
there again, say the quantum communication or quantum cryptography. So those kind of technologies they're supposed to come in the future.
Okay, sir. So any queries? Okay, sir. Thanks
Yeah,
for
yeah, okay.
thanks for your informative speech, sir, and also thanks for your valuable time spending with us. So
Thank you. Thank you,
okay.
Dr. Ashok, yeah, for giving me this opportunity. Thank you very much.
Yeah, thank you. Thank you very much, sir. Thanks to all participants. I will share the feedback link already in chat box. So I will post it in WhatsApp group also. Okay, all the participants, thanks for your time.
Yeah, Dr. Ashok, just one request. You
Yeah.
have shared that feedback. You can share with me also.
Yeah, sure,
Okay,
sir,
so
sure.
it will be for my improvement in future.
Yeah, yes, sir, sure, sir. Thank you. Can I wind up this session, sir? Okay, thank you. Thanks to all.
Yeah, thank you everybody for giving your valuable time, and thank you for being patient.
Okay, we will meet you all tomorrow. Thank you.